Alrighty, good morning everybody. Welcome back to Calc 3. Plan for today is I have a quiz for you on Standard 17, and then we're going to spend the rest of class today doing some review. And basically doing whatever you all would like to do for the rest of class. So I could do like a little, well, we'll talk after this. Office hours for next week are not going to be the typical office hours per se. They will be for Monday and Tuesday, but once classes stop, I might be changing up my office hours a little bit. I'll let you all know next week on that. But it will be the usual office hours on Monday before class and from 2 to 3. And as far as homework goes, keep in mind on Monday you will have exam 4, which will have a question from every standard, like the final. And just like the final exam, you can have 2 sheets of notes front and back for this exam on Monday. I just passed back the standard 16 quizzes. I'm still a little behind on the retests, but I'm planning on getting caught up on grading probably sometime tomorrow. And when I do, I'll update Blackboard with everyone's current mastery totals and send out an email to let you know I've done that, so that you know kind of where you stand going into Monday's exam. Any questions or comments before we get started for today? Yes, Emily. You can indeed do retests next week. Since my office hours are going to be at slightly different times later in the week, the retest times might be a little bit different, but yeah, you're absolutely welcome to schedule retests for next week. Any questions? All right, I've got a theorem for you. Here's the theorem. $1 is equal to 1 cent. And here's my proof. $1. Would you all agree that $1 is equal to 100 cents? And 100 cents is going to be equal to 10 cents squared, since 10 squared is 100. But 10 cents, that is a dime. And a dime makes up exactly $0.1. So we can swap out the 10 cents with $0.1. And if we take $0.1 and square it, we are going to get $0.01. But this is just 100th of a dollar, and what's the 100th of a dollar? That's going to be 1 cent.
Square dollars.
Say what?
Those are square dollars.
Oh, man, you figured that out way faster than the 8 o'clock class. I'll let them have to think about this until after the quiz, and they still couldn't figure out like what was wrong. I almost had them thinking this was correct. Good catch, Jack. Yeah. There is a couple issues here, which is namely saying that in the units, 100 cents is not equal to 10 cents squared, because I would say 10 cents squared is really going to be equal to something like 100 square cents. Whatever that is. Not your typical unit of money. So basically, this does not work. And for similar reasons, you can't say that $0.1 squared is going to be equal to $0.01. Really, this should be equal to something like 0.01 square dollars. Like if you take a dollar and you cut off part of it so it makes a square. But yes, the moral of the story is always be careful in watching your units. All right, let's do a quiz. Last quiz of the semester, I might add. Oh, what? Can be something I do. Just start in the middle. Go ahead and take a few seconds to finish up your thoughts. And pass your quizzes in, please. Pass your quizzes in, please. Here, I'll pick them up from you first. Okay, so the rest of class today, I thought we could just spend this class to kind of talk as a group to see what questions you all have about pretty much anything we've done over the course this semester so far. That means if you want to talk about some results, you want to kind of work your way through some practice problems, whatever you all would like. And to start off, I thought I'd just give kind of a quick reminder of all the things that we've done so far over the course of the semester. Just rack your memory. The first unit of the semester was sort of the pre-calc unit of the semester. And that was standards 1 through 5, where we talked about vectors, vector algebra, dot and cross products, lines and planes, as well as how matrices. Basically, all of kind of these tools that we ended up needing throughout the semester to do things using calculus. The second major unit of the semester was sort of the, I'll say, derivatives and limits part of the semester, which was standards 6 through 11. And that covered looking at properties of multivariable functions. So things like how do we find domain, how do we find range, how do we find codomain, how do we graph functions by looking at their level curves or contour curves. We talked about limits, continuity, derivatives, plus how to find tangent planes to a multivariable function, or tangent hyperplanes, depending on the dimension. We talked about derivative rules, like how to take higher order partial derivatives, how to do chain rule, etc. And finally, directional derivatives was standard 11. The third unit was optimization, which was standards 12 through 14. So for that, we looked about how to find local extrema of multivariable functions using the second derivative test. We talked about how to find do unconstrained optimization, where we had the process of finding critical points inside a set as well as on each of the edges. And we also talked about how to do constrained optimization using the Lagrange multipliers. And then more recently, we did integration for a couple of standards. 15 and 16, where we talked about how do you do double integrals, how do you swap the order of integration, how do you use polar coordinates to help integrate, and then kind of the last thing we just did, which was vector fields in standard 17, where we talked about things like how do you graph them, how do you find flow lines, which was on the quiz today, and finally, how do you find whether or not you have a gradient field. So what y'all like to talk about? Jackson? Finding range? Okay, so this is kind of a standard 6 sort of question. How do you find the range of a multivariable function? So let's go through a couple examples where we find domain, range, and codomain of a couple different functions. So let's see. Let's do one xy equals Let's start with an example like this, where we have a function f that's going to take in a vector with two components, x comma y, and it's going to spit out the vector as an output of x squared comma square root of y minus 1. And what I'd like to do is to find both the domain and the range, and I guess the codomain of this function. So what can we say about the domain? In other words, what can we say about the set of vectors that we are allowed to plug into this function and get an output that makes sense? Jackson?
The restriction is that y is
Why does y need to be greater than or equal to 1?
If y is less than 1,
Yeah, basically, we need y to be greater than or equal to 0, y minus 1 to be greater than or equal to 0, so we're not taking the square root of a negative number, which means y has to be greater than or equal to 1. Do we need any constraints on x? Emily? Doesn't look like it. If the only thing we're doing to x is squaring it, and you can square any number. So what can we say about our vectors? So how can we sum up then the domain of this function? What can we write out for the set of all the vectors that we're allowed to plug in? Brianna?
X comma y such that y is greater than or equal to 1.
Yeah, I would agree. Set of all vectors x comma y such that y is greater than or equal to 1. If you want, you could say x, y, and R2, but that's kind of assumed when you write out x comma y like that. Set of all vectors in R2 whose y component is greater than or equal to 1 in order to avoid this issue where we could end up taking the square root of a negative number otherwise. About the codomain. In other words, what's the Rn where all of our output vectors live?
R3.
R3? Why R3? Just feels like it should be R3?
Because that's y replacing z.
Don't think we can quite do that with this one, because it looks to me like our outputs aren't just going to be single scalar values. If we look at the types of vectors that are going to be outputs to this function, vectors of the form x squared comma square root of y minus 1. Ollie, where are those vectors going to live? I think the codomain is going to be R2 in this case, because each of these vectors, the vectors that we can get from taking outputs to our function, are all going to be two-dimensional vectors. In this case, the domain is going to be an R2 and the codomain, mainly because our function takes in vectors with two components to them and is going to spit out vectors that also happen to have two components to them. But since the outputs specifically are two-dimensional, our codomain is going to be an R2. How about the range of this function? Tom?
X is greater than 0, y is greater than 0.
Ah, you want to say that both of the output components have to be positive?
Yes.
Okay, so I think we're going to have a set of vectors in R2 where x and y are both greater than 0. Brianna?
I would say greater than or equal to 0.
Yeah, I would agree. I think it's possible to get 0 as an output for x. If for instance, our original vector had an x-coordinate of 0, our output vector would also have an x-coordinate of 0. And ditto with y, I think if we were to plug in y equals 1, for instance, into the original function, as our original vector into the function, the output vector would have a y-coordinate exactly equal to 0. since square root of 0 is 0. So in this case, I think our range would be sets of vectors in R2 both of whose components are greater than or equal to 0. Owing to the fact that x squared is only ever going to give you non-negative outputs, no matter what you plug in for x. And square root of y minus 1 is always going to be some positive number, no matter what you plug in for y, assuming you're plugging in something y greater than or equal to 1. Meaning there's no way to plug in anything for x or y that would make our output have a negative x component or a negative y component to it. Any questions or comments about that example? Jackson, would you like to see one more?
Yeah, just like range.
Range specifically? All right, let's do one with a little bit of a trickier range to it, maybe. Let's see. T equals. I'm going to go through domain because I know some of you have struggled with finding domain as well, and I think it'd be helpful to go through and do just a quick domain codomain range here. Lindsay, what's going to be the domain of this function? Okay, so what should I write out as our set?
It's going to be x, y, t, such that.
And we don't really have any conditions on our t. I would actually just say, easiest way to maybe write out our domain is to just say set of all real numbers. You're right, because our inputs are all scalar values. In other words, things that live in R1. And t can be any real number. We don't have t squared, 2t plus 1. We can do that to we can plug any number in for t into all three of those expressions. So I think our domain in this case is just going to be just all of R1. We don't need to restrict it in any way like we did with the domain of the last one. How about the codomain? John, any idea what we could say for codomain of this one?
It's going to be R3.
Yeah, I think so. Why R3?
Because you're plugging in one T and getting 3 different components.
Yep, it's because each of our output vectors happens to live in R3. It's a function that takes in vectors in R1, but spits out vectors in R3 specifically. All right, here comes the tricky one. What can we say about the range of this function? In other words, the vectors that you would actually get as being outputs of this function. I don't think the range in this case is going to be all of R3 because the three components are not independent of each other. If you know what the x component is of your output, that tells you something about what the y and z components are as well, for instance. So Jacob, what can we say about the range here?
You say that it's going to be x comma y comma z such that x is equal to the square root of y.
X is equal to the square root of y?
Yeah, or y is squared.
I like the second one better. Technically, if you wanted to say x is equal to the square root of y, you would need a plus or minus. Because it's totally possible to have a negative component of negative value for x and a positive value for y. So you can either say y is equal to plus or minus square root of x. I like y equals x squared just a little bit better, just because don't like having to write plus or minus if I can avoid it.
And then z will be 2x plus
1. Like that? Yeah, I totally agree. We know that whatever our x, y, and z components are, the y component has to be equal to the x component squared, because if whatever the x component is t, this y component is that term, but squared. And similarly, our third component, z of t, for z, has to be equal to 2 times whatever this is plus 1, which we can represent in the range as writing out z equals 2x plus 1. So, range is not going to be all of R3, specifically because x, y, and z are not independent of each other in this case. The x, y, and z components of our output vectors, I should say, they are all kind of related in the same sense that they're all coming from the same t that we plugged into the to the function originally. Yeah?
Can we go through determining if this function is continuous?
Sure. Let's wait just any questions about domain, codomain, or range of this function before we move on? Okay, so let's take a look-see. Is this function continuous? Do you want to look at this one specifically or just in general?
In general.
Okay. So, let me think. What would be a question I would ask on an exam if I'm doing this? Let's take a look at this function. F of x comma y equals x divided by x minus y. So, what does it mean to check for continuity with this function? Yeah, Doc?
I mean, essentially, if the limit from both sides as you're going along the equation essentially equal the same thing as long as it's range.
Both sides?
Yes.
I say if this is a Calc 1 function, I think we could say both sides.
Sorry, from all sides.
As I say, yeah, technically there's infinitely many sides you could approach points from, since this is a function taking in vectors in R2. And so I would say, yeah, I would just say that is f a continuous function? What that really means is it the case that at all values x comma y in the domain of f, meaning points where the function's defined, or let's say at all a, b in the domain of f, does the limit as x, y approach a, b of our function, f of x, y, exist and equal f of ab. Because that's what we would need for f to be a continuous function, is that at any point where this function is defined, meaning I think at any point where x and y are not equal to each other, will it be the case that the limit of our function both exists and is equal to what we would get if we were to plug in ab into the function? Jacob?
Yeah.
You think so?
As long as you're in your domain, you can just direct sub anything into that. And so that'll make your limit really easy to solve. if I just use the value.
Yeah, I would agree. I think we can say that for all A, B in the domain, meaning at all points where A and B are not equal to each other, we need A to not be equal to B because otherwise we'll get a 0 in the denominator. Don't divide by 0. I agree with what Jacob said. I think we could just take the limit directly. Limit as xy approaches AB of x over x minus y. We can just plug in A and B, and we'll get A over A minus B, which is just f of AB. Yeah. At any point where this function is defined, we can take the limit by just doing a direct substitution. So f is going to be continuous. So f is a continuous function. I would agree. A follow-up question, though. Is f continuous at -2, -2? Alan, what do you think?
No, because the denominator would be 0.
Yeah, so f of -2, -2 isn't even defined?
Yeah.
I would agree. No, as f of -2, -2 does not exist. And if you remember back to what do we need for continuity, at a point, the first thing we needed is that the function is defined at that point. And then also that the limit exists at that point and that the value of the function is equal to the limit. So what gives? Why is it the case that f is a continuous function, but it's not continuous at -2, -2? Yeah?
-2 is not in the domain of that.
Indeed. Yeah. The reason why this right here doesn't cause f to fail to be a continuous function is because this isn't a point that's in the domain. Jacob, what you were saying earlier is that if you were to take any point that is in the domain, like say any point where A and B are not equal to each other, the function's going to be continuous there, which makes this a continuous function. The problem though is that here we have a point where the function isn't continuous, but it's not a point in the domain, so it doesn't affect continuity of the function as a whole. Doesn't affect continuity of f as a whole, since -2, -2 isn't in the domain. So it's totally possible to have a function that is a continuous function, but not continuous at some point outside of its domain. Because by definition, if it's outside the domain, then the function can't possibly be continuous there. One more quick example before we move on from continuity. Let's say we had a piecewise function, like g of x, y, z, and just g of x, y, equals x squared minus y squared over x plus y if xy is not 0, 0, and 10 if xy is equal. If we wanted to determine whether or not this function is a continuous function, what would we have to do? Jacob?
You have to see what value the top piece of the piecewise function is approaching at 0, 0.
Okay.
And if it approaches 10, then it's continuous.
Okay. So there's some worry about whether or not this function is maybe continuous at the origin. So let's check. Is g continuous at 0, 0? Well, if we were to take a limit as xy approached 0, 0 of g of xy, we would need to get a limit as xy approached 0, 0 of x squared minus y squared over x plus y, as you pointed out, Jacob. What can we do if we wanted to evaluate this limit? Limit as xy goes to 0, 0 of x squared minus y squared over x plus y. Yeah?
Evaluate it along different lines that cross through the point 0, 0 and see if all those limits are equal to each other.
Okay, so you want to evaluate some limits along a few different directions. Katie?
Factor out back to the top into x plus y, x minus y.
Ooh, we could also do that. I like that idea. I'm gonna do that, and then down if you want, we can come back and look at a few different directions here in a second. So Katie noticed that we can factor the numerator of this expression into x minus y times x plus y. And what can we do with that? Huh?
Divide x plus y.
Give it the old swoosh swoosh. And when we do that, we'll be left with a limit as xy goes to 0, 0 of just x minus y.
And then we can just direct sum and
Yeah, at this point, we could just plug in 0 for x and y, and it turns out that the limit came out to 0. So, Olivia, what do you think? Is this function going to be continuous at the origin?
No, because it doesn't approach 10.
Yeah, it's because the limit as xy approaches 0, 0 isn't the same as g of 0, 0. So no, g of xy is not continuous at the origin, since the limit as xy approached 0, 0 of g of xy was not equal to what you get when you just plug in 0, 0 into the function. Because this expression came out to 10, and this limit came out to 0. Is g a continuous function as a whole? Emily? Yeah, it's because 0, 0 in this case is a point in the domain at which our function is not continuous, and that's enough to cause g to not be a continuous function. So no, because 0, 0 is a point in the domain of g where g is not continuous. In the previous example, it was a continuous function even though there were points where the function was undefined, because in the example before this one, anywhere that the function was defined, it happened to be continuous. Whereas in this example, we found a point, namely 0, 0, where the function is not continuous. And since it's not continuous at the point 0, 0, which happens to be in the domain, that's going to be enough to make g fail to be a continuous function. Jackson, you have a...
Is it right to think that because 0, 0, 10 isn't connected to the rest of the graph? Is that why it's
Correct. If this was like a Calc 1 sort of function, it's not, but if it was, it would sort of be an example of something that looked like this. Where you sort of have a hole in the function at, well, pretend that's the origin. Where at this point, where it's nice and continuous everywhere except for this one point, where the limit as x approaches, say, 3 of this function exists, but it's not equal to the value of the function at that point. We have something sort of similar going on here, where technically this is a plane, actually, except at 0, 0, the point is taken 10 units higher than where that plane actually lies. That's a good kind of geometric way to think about what's going on here. Any other questions about continuity? Or ready to move on? So that was standard 6 and 7 just now. What else would y'all like to talk about? Holly?
I know this was basically like last class, but can you go over if the vector field is a gradient field and like how to find it?
Yeah, sure. So jumping from standard 7 to standard 17. Let's take a look at a vector field and see if we can determine whether or not it's going to be a gradient field. This one, I'm going to pick an example out of the book. How about we look at the vector field? Let's take a look at this example. X squared cosine y plus 3y, comma, xyz. So here we have a vector field. It's going to be a function going from R3 to R3. And we'd like to see, is this a gradient field? Meaning, can we find a function little f which will have to go from R3 to R, where the gradient of little f is equal to big F. If the answer is yes, then big F is a gradient field, and little f is a potential function for big F. And if we can't find any little f where this works out, then big F is not going to be a gradient field. So, what do we have to do to determine whether we can find some little f whose gradient is equal to big F? Bob, what would be like a good first step?
Set up the unintegral
Yeah, because if the answer is yes, this would have to be equal to little del f del x. This would be little del f del y. This would have to be little del f del z. And so if we integrate each of these pieces with respect to the appropriate variable, that should tell us something about the original function f. Little f, whose gradient would be our vector field capital F here. So let's see what happens if we do that. So if del f del x is equal to 2x times sine of y, what would f of xyz would have to be some antiderivative of 2x sine of y taken with respect to x, since its derivative with respect to x is 2x sine y. And if we integrated 2x sine of y with respect to x, what would we find? Olivia?
X squared sine of y
X squared times sine of y?
plus g of y.
Yeah, plus potentially some terms with y's and z's showing up inside of them. So what this tells us is that f has to have a term that is x squared sine of y, and any other terms that show up in our formula for f can only have y's and z's in them. And, I guess, constant values. So if del f del y is x squared cosine of y plus 3y, that would tell us that our function f has to be some antiderivative of x squared cosine of y plus 3y taken with respect to y. And what would an arbitrary antiderivative of x squared cosine y plus 3y taken with respect to y look like?
X squared sine y plus 3 halves y squared plus
Let's say h.
Yeah, h of x and z.
I like it. Yeah, nice job. Our formula for f, in other words, has to have an x squared sine of y term. It has to have a 3 halves y squared term. And any other terms that it has can only have x's and z's in them. There can't be any other y terms showing up. Katie, have we seen anything yet that would cause us? Is this compatible with this? Meaning, from what we've seen so far, is it possible still that there's a function that's of both this form and that form?
Yes, y is 0.
I think the issue is if y is 0 necessarily. Because we have to think about, we're not plugging in specific numbers for x, y, and z here. We need something like the general form of a function. But honestly, I think everything so far is okay, because if, for instance, we had something like f of x, y, z is x squared sine of y plus 3 halves y squared plus 1, that would be a function that would look like this, meaning its only x term is an x squared sine of y term, and everything else is just y, z's, and constants. It would also be a function that looks like this, where the only y terms are x squared sine of y plus 3 halves y squared, and everything else is just x's, z's, and or constants. We still need to check our del f del z, though, see if this works. So if we try that, we would get del f del z would have to be xyz, meaning an f would have to be an antiderivative of xyz taken with respect to z. Tim, what would an arbitrary antiderivative of this with respect to z look like?
I'd xyz squared divided by 2
Yep, 1/2 xyz squared.
plus
I'm gonna call it k.
k of xy.
I like it. Yeah, plus some expression that only has x's and y's showing up inside. So here's the question, Holly. Is it possible for a single function, little f, to have all three of these forms?
I don't think so.
Why not?
Because in the last term it's 1/2 of xyz squared, and then before you only established that you only have y's and z's. That has 1/2 x. Is that what it's talking about? Okay.
Yeah, I think you're absolutely right. I think this term right here is going to cause us some grief. Specifically because what we found here told us that the only term that can have x's showing up in it is a term that has x squared sine of y. But this is another term, but here we're saying our function has to have another term with x's in it, namely 1/2 xyz squared. And we could also say that that doesn't work with this one, because here we have that our only terms with y's in them are an x squared sine of y term and a 3/2 y squared term. Whereas here, we have another term with a y in it that's not of this form. So I think we can say the answer in this case is big F is not a gradient field. Since if, let's say, F's only term with x's is an x squared sine of y, F cannot possibly have a 1/2 xyz squared term showing up. So in this case, F would not be a gradient field. I'm going to make a slight tweak to this, just so I don't have to start over from scratch. I'm going to make a slight tweak to this vector field that would make this a gradient field. And then we'll practice finding a potential function. So let's say if instead of xyz, it was z squared minus 1. So the first two terms are the same, meaning f still has to have this form and this form. But now we're going to assume that our del f del z term, del little f del z term is z squared minus 1 instead of what it was before. So in this case, if f was an antiderivative of z squared minus 1 taken with respect to z, Lori, what would be the general form of f according to this?
1/3 plus k of xy.
I like it. 1/3 z cubed minus z plus some whatever's left over can only have x's and y's showing up inside. And I think in this case, we can say that f is that we can find a function little f that has all three of these forms. Madeline, what would be a function little f that we could say satisfies all three of these conditions?
X squared sine y plus 3/2 y squared plus 1/3 z cubed minus z.
Like that? I like it. It's a function whose only x term is x squared sine of y. The only y terms are x squared sine of y plus 3/2 y squared. The only z terms are 1/3 z cubed minus z. I think this is going to work. Yeah?
Could there be a possible constant?
We could. Now give me a constant.
C.
Pick an actual number.
4.
That would also do the trick. I want a specific constant so we can say this is a single potential function. But yeah, I think this would work. Is a potential function for our capital F. So capital F is a gradient field. It is a conservative vector field in this case, because we were able to find a potential function. Madeline, your version without a constant works just as well. Because that constant can always be folded into it's part of the stuff that doesn't have x's. It's part of the stuff that doesn't have y's. It's part of the stuff that doesn't have z's to it. Or if you want to be like Brianna and have a constant term, you can as well. It would still be a potential function. Because all of its partial derivatives happen to match up with the terms of our vector. Does that help clear up some of your confusion, Alan? We're about out of time, but we can do like one more sort of quickish question. Luke?
Can we just listen to this quick review of the multivariable chain rule?
A quick review of the multivariable chain rule. Oh boy. Okay. That is all right, a standard that took us 2 classes, a quick 2-minute review. So multivariable chain rule basically says that if you have a function f that's going from some, let's say, rn to some rk, and g, let's go get these lowercase letters. F is going from some m to some rn, meaning the composition of the two is going to go from rm to rn, and from rn to rk. So this will be g, this will be f, this will be f composed with g. Then what the multivariable chain rule tells us is that the derivative of what happens when you take f composed with g of a vector x, where x is in Rm, is going to be the same as if we were to take the derivative of f evaluated at g of x, multiplied, and this is matrix multiplication, multiplied by the derivative of g, taken with respect to x. So basically, in other words, if you take the matrix corresponding to the derivative of f, evaluated at g of x, and if we multiply by the matrix corresponding to the derivative of g, that should give us the same matrix. That's the derivative matrix of f composed with g. That's the multivariable chain rule in a nutshell. Fortunately, we're about out of time for today for looking at more examples. Luke, if you want to, if you have any more specific questions, Luke, send me an email. I'll be happy to kind of talk you through, because this also had the sort of variant where we went from R1 to Rn to R1 word problem variant that could very well show up on the exam as well. Have a good weekend, everybody. See y'all on Monday.